All right, great. Thank you, Darcy, and thanks to everyone who's dialed in today or logged in today for the webinar. And just a reminder, if anybody does run into technical difficulty, I know we've already passed the slide with the technical assistance number, but if you go look in your chat window, you can find the phone number there for technical assistance. So, for example, if Matt or I drop out, you can't hear us, just give that number a call and we'll get it sorted out. Now, for those of you who participated in previous webinars in this series, you might recall that we began with a webinar that described the risk of drinking water contamination and some very basic things that water utilities could do to prepare for that risk. Then in the following 10 webinars, we had speakers from water utilities, other water sector partners, and EPA cover specific components of surveillance and response systems. And these included online water quality monitoring, either in the source water or the distribution system, monitoring the physical security at remote utility facilities, and using customer complaint surveillance and public health surveillance to detect possible water quality problems, and of course, response planning. Now, implementation of any of these single surveillance or response components is certainly beneficial and worth pursuing. But what we're going to talk about today is the increased value that can be derived by deploying an integrated surveillance and response system that involves multiple components. And just to be clear, here's what we're talking about when we're referring to an integrated or comprehensive surveillance and response system. It includes both surveillance and response components, and the use of multiple independent surveillance components does provide several advantages. For one, it increases contaminant coverage because these different components do have different capabilities for detecting different types of contaminants. Furthermore, a system like this with multiple surveillance components can provide more timely detection because depending on how a contamination or a water quality problem unfolds, one or the other surveillance component is more likely to provide an indication earlier. You can also achieve broader spatial coverage. And importantly, you can increase your strength of signal or your confidence that something's actually happening in the system that warrants some attention if you get information from multiple independent surveillance components. In the architecture, data from these surveillance components are monitored in real time, and an alert would be generated when an anomaly is detected. Then the alert would be investigated to try to determine whether or not it's a serious water quality problem like contamination. And if contamination can't be ruled out, then we move into the response phase, where we would implement sampling and analysis activities to try to pinpoint what the problem is. And water contamination response plans would be implemented to try to minimize any adverse impacts from a contamination incident. And now we'll go ahead and open the second poll question, which will focus on surveillance components. So please tell us which of the following surveillance components your utility is actively using. And we're aware that implementation of any of these components can vary significantly with respect to its level of sophistication. So as you answer this question, consider whether or not your utility is operating at least one online water quality monitoring station in your distribution system. For physical security monitoring, are remote facilities equipped with intrusion detection systems? For customer complaint surveillance, do you have a mechanism to monitor and track unusual volume or clusters of water quality complaints? And finally, for public health surveillance, does your utility have a procedure in place such that they would receive prompt notification from their public health partners if they suspect a waterborne disease outbreak is occurring? And finally, there's another option. So if your utility is doing another form of surveillance, we like to hear about it. So just enter that write-in response into the questions window. And Emily, we'll give that a few more seconds for people to wrap up their responses. And once they're done, we'll share the results. All right, great. So what we see is we've got a lot of the audience, almost 2/3 doing water quality monitoring, physical security monitoring, and customer complaint surveillance. maybe about a third, a little over a third doing public health surveillance, and we had some write-in votes that will, or write-in responses that we'll look at later. But this is encouraging. It means we have a very proactive group of attendees during today's webinar. So as we go through the rest of the presentation, maybe just consider how the information we're providing could help you to increase those surveillance capabilities and maybe integrate them with other data streams. So in thinking about how to design an integrated surveillance and response system, recognizing that it can be a very involved process, we want to lay out a systematic process for doing that. And it begins with establishing an effective project team that would include a designated and strong project leader, as well as teams that are assigned to develop each of the individual surveillance and response components. We found that's an effective way to structure the team to allow people to focus on specific technical tasks. It's also important to establish design goals that describe what the system is intended to do for your utility, as well as performance objectives that document how well the system needs to function to realize those benefits. As with every project, we need to identify constraints, typically budget and schedule are big ones. And once those preliminary activities have been completed, we can go to the component teams and ask them to assess existing capabilities within the utility or within partner organizations that can be used to start to build the surveillance or response components. Now, in many cases, there'll be a strong foundation, but gaps might be identified, and then possible enhancements can be derived from that gap analysis. So collectively, taking the goals, objectives, constraints, and gap analysis, you can then start to develop preliminary component designs and also information management requirements. And we'll say a lot more about that later. And finally, all of that information can then be rolled up and brought back to the project team as a whole, where design alternatives can be evaluated, and then the best design can be selected for implementation. And what we'll do is we'll use this process as sort of a roadmap for the rest of the presentation. We'll kind of go through each one of these steps in the overall process diagram. So starting with building the team. Again, implementation of an integrated surveillance and response system with multiple components will almost certainly require a multidisciplinary team that would include personnel from multiple utility divisions. This could include operations, engineering, water quality, security, information technology, and finally customer service. Likewise, especially when you get to the response side of the program, the project team will almost certainly need to engage with external partners. And some common partners that have been engaged with for these types of response planning activities include local fire departments and hazmat responders that might support various field operations during an emergency, emergency management agencies that can help coordinate response activities. You also need laboratories that are capable of not doing just the routine analysis, but doing analyzing water samples possibly for unusual contaminants, or maybe in greater volumes than are normally handled, or with more rapid turnaround times than are typically expected. Of course, there are local and state health departments that would help coordinate public health response actions. And finally, drinking water primacy agencies that would certainly be involved in key response decisions. And with that sort of introduction to the response partners, let's open up another poll question. Oops, sorry, went too far. So with the previous question, we asked about the surveillance components. Now we want to know about your utility's response capabilities. So please click the capabilities your utility currently has to respond to a contamination incident. And for the response plan, we're aware that most utilities should have an emergency response plan. But consider whether or not you have either an annex to that plan or more specific plans for dealing with contamination. Same thing for sampling and analysis. Every utility has basic capabilities for doing those functions, but do you have the maybe augmented capabilities that would be necessary during a contamination emergency? Incident command structures are important for assigning roles and responsibilities during an emergency, and certainly for interfacing with other response agencies that live by ICS structures. And finally, we just went through several response partners that would be needed to support response activities. So consider whether or not you have a sufficient response partner network to support those response activities. And again, if you have other response plan or response capabilities that aren't covered here, please write those in. So we'll give it this another few seconds to wrap up and then take a look at the results. All right, excellent. This is great to see. Again, we have most of our audience today has very good response capabilities. Sampling and analysis might be the weak, I don't want to say weak, but the fewest people indicated they have that capability. And if you're interested, we do have guidance for how you could build up that capability, and we'll get to that, where that guidance resides at the end of the presentation today. So let's go on to the. All right. So the next step in the process after you have your project team, including considering the need for coordinating with external partners, is to establish specific design goals. And these design goals, again, are intended to capture the desired benefits that are realized by operating a surveillance and response system. And to the extent possible, they should be as clear and precise as possible, because the more focused they are, the better they can serve as a tool for actually making design decisions, maybe about which components to include or what capabilities to invest in. And this word cloud shows several design goals that utilities we've worked with over the years have identified. And while detecting contamination incidents is certainly a common and important design goal, it's certainly not the only one that utilities have identified. And in general, the more design goals that you can lay out that are achievable, the stronger the business case will be for maintaining your system. And it's also a good idea to develop performance objectives that establish the criteria that the system would need to meet in order to achieve the design goals. And a few examples would be data completeness, data accuracy and precision, the frequency of invalid alerts or false alarms, the amount of acceptable instrument downtime, and hand in hand with that is the O&M requirements, including both the labor and the cost to maintain the system. And finally, the time it takes to investigate alerts and respond to serious water quality problems. And the helpful thing about establishing clear and meaningful performance objectives is it can help you to determine whether or not various solutions to your design problem are going to be adequate. And in some cases, they might lead you down a path where a simpler or less expensive solution is adequate, so that you don't overspend or overbuild on a project. As with every good project, unfortunately, we have constraints, and we need to identify those up front to make sure whatever designs we come up with are going to be feasible to implement. And the one that comes up first is capital budget. So how much money do you have to spend to build out the project? But of course, operations and maintenance costs are another important constraint. And what we found with the big systems that have been implemented by utilities in the US is that oftentimes over the life cycle of the project, the O&M costs are greater than the initial capital costs. So it's important to take a look at the whole life cycle, of course. Also consider the availability of essential personnel. For most utilities, this is a discretionary activity doing this kind of advanced surveillance and response planning. So make sure that the key people who need to work on this project do have some time that they can commit to this and still fulfill their day-to-day jobs and duties. And finally, there may be policy restrictions that could shape or even limit the design of the system. Common ones we've found that have been caused some restriction have been IT restrictions. And we've encountered cases where utilities have wanted to, for example, get remote access to various data streams, but the IT restrictions prevented that. Or or at least cause the utility to have to consider a workaround solution to get access to that data. Same thing with building codes. If you're going in and installing equipment, especially in a non-utility facility, you might have additional constraints on how you do implement those systems. And finally, contractual requirements, which could impact not only who you can select to do a job, but how long it may take to get that contract in place. So the next step in the process is to conduct an assessment of existing resources and capabilities that might be leveraged for a surveillance and response system. And for this portion of the presentation, I'll turn it over to Matt Umberg. And Matt, I just gave you mouse control, so you should be able to run it.
Okay, thanks, Steve. Let's see. Okay. All right, well, thank you, Steve. So most utilities have existing capabilities that can provide a solid framework for an SRS. To help utilities identify and assess these capabilities, EPA has developed the SRS Capabilities Assessment Tool. This tool walks users through a simple set of questions to assess their existing surveillance and response capabilities that can be leveraged for an SRS, and generates customer reports that present potential enhancements and technical resources for implementing those enhancements. The tool consists of 6 modules, 1 module for each SRS component. The design and process followed by each module is the same. To show how the tool works, we'll first work through the water contamination response module. Each module is organized according to a component's design elements or subject areas. This is an example of a design element intro screen that signals the beginning of a new design element section. At the top of the screen is shown the module name, and that is consistent throughout the module, but the content card below it, at the top of the card is shown the design element name, and below the design element name is design element background, just providing a little bit of background information to get you familiar with the subject area before you continue and start answering questions. So for this design element, we're looking at the response plans and procedures design element, and the intro text is effective response to a contamination incident in a distribution system requires the use of response plans and procedures. A utility's emergency response plan covers basic response functions, but it lacks specific procedures for responding to a contamination incident. Thus, supplemental plans and procedures should be developed to guide investigations, response, and management of resources during contamination incident. So the final piece of the design element intro screens is a statement of target capability. And a target capability is a level of performance or outcome necessary for an effective component. So for this design element, the target capability is plans and procedures for responding to a contamination incident in a distribution system have been developed. Okay, so now we get into the questions related to that design element. So at the top of the screen or the top of the card, we have the design element name and we have the question. So the first question for this design element is, does your utility have plans and procedures for responding to a contamination incident in the distribution system? We then have response choices. In this case, it's a yes/no question. Most of the questions within these modules are yes/no questions or multiple choice questions. And then finally, for each question screen, there's a bit of context that's provided. This context provides information that shows why the question is being answered in the first place, why it's important to the process, in addition to providing additional information to better understand either the question or the response choices. So for this question, the context is plans and procedures that may be relevant during a contamination incident include cross-connection control plans, emergency sampling procedures, water use restriction notification procedures, and plans that deal with specific contaminants or water quality problems, like cryptosporidium, red or rusty water incidents, or nitrification. For this walkthrough, we'll answer no, we do not have plans or procedures. And then we move on into the next design element intro screen. And I'd just like to note really quickly that the exact sequence of questions that's presented during a given assessment is related to our responses during the assessment. So here, for the first question, we responded no, we do not have plans or procedures. So any follow-on questions that were relevant to plans and procedures were no longer needed and no longer presented. So we move on to the next design element, which is response partners. And the intro text is WCR relies on a utility's response partners to assist during a response to a contamination incident in a distribution system. While a utility can prepare for such an incident, it will rarely be able to handle all contamination scenarios alone. Response partners provide additional personnel, equipment, resources, and expertise to bolster a utility's capabilities and ensure an effective response. And the statement of target capability for this design element is response partners have been identified and engaged to support a coordinated response to a contamination incident in the distribution system. So let's move on to the questions for this design element. First question is, has your utility identified response partners who can assist during a response to a contamination incident in the distribution system? Again, this is a yes/no response. And the context is identifying response partners in advance of an emergency reduces the time needed to receive assistance. Partners can include local and regional responders like local law enforcement, fire departments, health department, hazardous materials units, other water or wastewater utilities, or support laboratories. Also, state agencies like primacy agencies, state health departments, and National Guard, and also federal agencies like EPA, CDC, FBI, and DHS or FEMA. For this example, we'll respond yes, we have identified response partners. So a follow-on question is, has your utility engaged its response partners to plan response efforts for a contamination incident in the distribution system? Again, a yes/no response. And the context is planning with response partners ensures a coordinated response that all parties understand what is expected from them during an emergency. This planning should consider notification and communication procedures, available resources and personnel, authorities, and roles and responsibilities. And we'll answer no for this question. And that's it for that design element. So now we move on to the third and final design element for this component. And this design element is training and exercises. So the intro text is, once planning for WCR is complete, practicing with response partners is necessary to effectively use response procedures during an actual contamination incident. Training and exercises provide an opportunity for utility personnel and response partners to learn and practice procedures in a no-fault environment to improve their understanding and execution of response actions. And the statement of target capability for this design element is, regular training is provided and exercises are conducted for utility personnel and response partners to prepare for responding to a contamination incident in the distribution system. The question for this design element is, does your utility provide regular training to its personnel for responding to a contamination incident in the distribution system? Again, a yes and no question. The context for this question is, training should cover all elements of your utility's response plan, including the command structure, investigation, operational responses, risk communication, public notification, and remediation and recovery. Basic orientation and refresher training should occur yearly, while more complex training or exercises should occur on a multi-year cycle. And for this question, we'll answer no. And that's it. For this module, we just had 4 questions given the responses that we provided. And for all of the modules in the Capabilities Assessment Tool, you'll probably be presented with anywhere between maybe, say, 4 questions on the lower range to maybe up to 15 questions on the higher range. In most modules, you'll probably see anywhere from like 5 to 8 questions. So given that you know the answers to the questions at the time that you complete the assessment, you should be able to complete an assessment within, I think we just ran through that in about 7 or 8 minutes. So it's a pretty quick process for going through an assessment. Once you finish your assessment, you can click Generate Report. And the tool generates a Capabilities Assessment Report. And the report is a PDF file that the main body of content is a series of tables, 1 table for each design element. So let's walk through these tables. At the top, the header row of each table is design element covered within that table. Below the header row is the intro text for the design element again for your future reference. I won't read through that now. But below the intro text is an assessment of your utility's existing capabilities. So first we have the target capability, which again, for this design element, is plans and procedures for responding to a contamination incident in the distribution system have been developed. And the target capability, as well as the intro paragraph above, is static for every time anybody would go through this module. Regardless of what our responses are, those stay the same. The customized feedback starts with the existing capability and assessment. So for that, we have, you indicated that your utility does not have plans and procedures for responding to a contamination incident in the distribution system. These plans and procedures are needed to ensure a coordinated and effective response and to minimize response and recovery times. Okay. So given the difference between our target capability and our existing capability for this design element, 1 or more recommendations are provided. In this case, there's a single recommendation that's provided, and that is to prepare plans and procedures. We can create a distribution system contamination response procedure and a risk communication plan to guide our utility's response to a contamination incident in a distribution system. Collectively, these documents should cover the following topics, and then there's a list of topics. So for each recommendation that's provided, there are 1 or more resources listed that can help you implement that given recommendation. For this recommendation, there are a series of 3 resources provided. And recommendations can range from guidance documents to tools to links to other types of resources. So for this design element, for this recommendation, we have 3 potential resources. First, guidance for responding to drinking water contamination incidents. Second is planning for a contamination primer. And then third is developing risk communication plans for drinking water contamination incidents. And each resource has a description that describes how the resource can be used. So that's it. That's the table for the first design element. We'll move on to the second design element, response partners. Again, we have the design element name. We have the design element intro paragraph for the assessment of existing capabilities. Again, the target capability is response partners have been identified and engaged to support a coordinated response to a contamination incident in the distribution system. Now, given our responses to the assessment, our existing capability and assessment is, you indicated that your utility has identified response partners, but it has not yet engaged them to prepare for responding to a contamination incident in the distribution system. Working with response partners to prepare for an incident ensures that all efforts are coordinated and all parties understand the expectations during an emergency. Now, given our existing capability and the target capability, Again, we're provided with one recommendation, and that is to engage response partners. We can identify capabilities and clarify roles and responsibilities for responding to a contamination incident in the distribution system. Details to discuss include notification and communication procedures, available resources and personnel, authorities, and roles and responsibilities. For this recommendation, we're presented with two resources. The first is guidance for responding to drinking water contamination incidents. And I'd like to point out really quickly that, like for this resource, you see we refer specifically to an individual section within this report. For all the resources, we try to identify the most specific piece of guidance that's related to the recommendation being cited. So in some cases, an entire document is relevant to the recommendation. In some cases, there could be one or more sections. So that's specified in here to be able to help pinpoint the most specific piece of guidance possible. So the second resource is Planning for a Contamination Primer. So that's it for the second design element. For the third design element, training and exercises, we have the introduction paragraph. For the assessment of existing capabilities, we have, again, the target capability. Regular training is provided and exercises are conducted for utility personnel and response partners to prepare for responding to a contamination incident in a distribution system. Okay. Then based on our responses in the assessment, our existing capability and assessment is, you indicated that your utility does not provide regular training to its personnel for responding to a contamination incident in the distribution system. Training and exercises allow personnel to learn in a no-fault environment, and they provide opportunities for improvement. Okay, so given our existing capability for this design element, two recommendations are provided. The first recommendation is to provide training and exercises. We can provide regular training and conduct exercises for utility personnel for responding to a contamination incident in the distribution system. Resources provided are, first, guidance for responding to drinking water contamination incidents, and second, the Water Quality Surveillance and Response System Exercise Development Toolbox. The second recommendation is to train with response partners, and we can include response partners in any activity or decision that requires their involvement. And the single resource that's provided for this recommendation is guidance for responding to drinking water contamination incidents. And that's it for the main body of text or the main body of content for this report. That's it. We had the three tables, one for each design element. The next steps outlined at the end of the report are to select which recommendations we would want to explore and possibly implement, and to document the design of our component in a component improvement plan. And in some of the component modules, there are templates for starting these design documents. And then finally, at the very end of the report is a resources section. So any resource that is included in our specific report that was just generated are just summarized at the end for your future reference. So that's it for the walkthrough for the Capabilities Assessment Tool. I'd encourage you, if you have, even just 20 minutes or so, if you are interested in one or more SRS components, to check out our website to access the tool and just play around a little bit and see what types of recommendations could be applicable to your utility. And I think a link for the tool will be provided in the upcoming slide. So that's it for the SRS Capabilities Assessment Tool. Steve, I'll send it back to you.
All right, thanks, Matt. So Matt mentioned that many of the guidance documents we provide do have templates for preliminary component design documents. And an outcome of working through the Capabilities Assessment Tool that Matt just walked through are a set of recommendations. Of course, it's completely up to a utility which recommendations, if any, to pursue. But what we would suggest, if any recommendations are selected for implementation, that those be codified in a a simple design document. And the templates that we provide in various guidance documents for these simple design documents or design plans they include basic elements such as preliminary information flow diagrams that show how information travels between systems and gets to users. There is also a section for developing a preliminary alert investigation procedure. And we found that this is helpful to do earlier in the design process because it can shed light on the kinds of information and the form in which that information needs to be accessible to the people who are responsible for conducting the investigation. The design template also has a section for documenting personnel who would be responsible for designing and implementing the system. If it's an equipment-heavy component, there would be a section for outlining equipment options. Same thing for data analysis methods, and this could include things such as anomaly detection systems or alert thresholding logic that would be necessary to generate the alerts that are then investigated. And finally, of course, there would be the required budget and schedule elements of those preliminary designs. Also, for any surveillance and response system, really no matter how complex or simple, information management is going to be an important element of that. And a well-designed information management system should provide timely access to the data and present it in a usable format such that it allows the user to monitor real-time system conditions, investigate component alerts, and if there appears to be a problem in the system, to respond to that problem in a timely and effective manner. So in order to develop an information management system that meets the needs, it's very important to clearly define the requirements for that system and do it up front. And this sounds trivial, it sounds obvious, but for those who haven't gone through the process before, it can be an involved and in some cases time-consuming process, but it's worth doing. Generally, we look at requirements in two different categories: functional requirements and technical requirements. So functional requirements are those features that are important and visible to the end user. And examples of functional requirements might include the manner in which data is accessed and displayed to a user, the way by which they get critical information such as alerts. On the other hand, technical requirements are often operate behind the scenes, but they're essential for having a stable and reliable information management system. And examples of technical requirements could include data communication protocols, cybersecurity features, and backup and recovery systems and protocols. And again, what we found is a set of well-crafted requirements is really important to selecting the best solution for the job. And to assist users in this process, we have developed a tool called the Information Management Requirements Development Tool. Okay, not very creative, but it's to the point. And at the end of the webinar, we'll provide a link to that tool. And what it does, it's nice in that it helps users to start to think about and identify useful information management requirements, organize them, consolidate them, and prioritize them, and then finally document them so that they can be used to inform a design or can be included in a bid document. So depending on the components that are included in a surveillance and response system design, there are a number of source data systems that might be utilized. Most of them would be internal to a utility, like call and work management systems. Well, these are all systems we've seen leveraged. So call and work management systems, SCADA or operational control systems, GIS platforms, laboratory information management systems, and water quality databases. And of course, business enterprise systems, even if they're not used for like a core technical function, often serve a background function in the system architecture. And in some cases, external systems can be leveraged as well. Public health surveillance is always operated outside of a utility, but some utilities have found a way to work with their health partners to pull in at least basic alert information when there is a public health surveillance alert of interest. And in other cases, we've seen city IT infrastructure leveraged to for functions like remote communications and data transmission. saving the utility some time and resources in building that piece of the architecture. So once the requirements and the source data systems have been identified, it's time to find a solution or select a solution. And without going into a lot of detail, just sort of sketching out at a high level, we see that in some cases, very simple tools or solutions can meet the requirements. We've seen tools as simple as Excel tables with embedded macros that do a time series display, maybe have periodic pools of data to refresh the information that's presented. On the other hand, if you're designing a multi-component system that's working with a lot of different types of data, it might be beneficial and it might be essentially necessary to meet the requirements to develop more of a dashboard type of system. And these dashboards are quite effective for displaying multiple data sets in a meaningful way. And a well-designed dashboard should give a viewer a broad overview of system conditions at any time, but allow them to easily drill down to details for essentially any point on the map. And when we first started doing this work, these systems were time-consuming and expensive to develop. But that was 10, 12 years ago. Nowadays, there's been a proliferation of dashboard solutions, and there are consumer off-the-shelf softwares out there that can serve as a dashboard very effectively. And so they're much less expensive, much easier to customize without having a PhD in computer science. Now, as you work through the design alternatives or design process, no doubt you'll come up with some alternative design options. And these alternatives could range across all scales of the system. At the highest scale, you might come up with completely different system configurations that you want to consider that involve use of different surveillance or response components. At a component level, you might have different component designs. Let's take online water quality monitoring as an example. You might be evaluating one design that has just a few very high-end, sophisticated monitoring stations, and you want to compare that with a system that has a larger number of monitoring points, but with simpler or maybe fewer online instruments at each site. And finally, at the subcomponent level, you might be wanting to evaluate different types of equipment, like different chlorine residual monitors. So to work through this in a objective way, we want a systematic approach. And so there are many alternative analysis schemes out there. The one that we use involves calculating a life cycle cost estimate in one column and a capability score in the other column. So for life cycle cost estimate, we consider the basics, implementation costs, O&M costs, renewal costs, and the value of remaining useful life in any assets that are deployed. Then the capability scoring criteria requires a little more creativity. And some generic ones that we can throw out for the purpose of an example are, you might want to evaluate options with respect to their detection capabilities, spatial coverage, the timeliness with which they provide information to users, how easy they are to use, how reliable they are, and so on. So what we do is we compute those two values for each alternative, a life cycle cost estimate and a capability score. But then we're left with two pieces of data that are in different units, essentially, for each alternative. So we need a way to reconcile that. One simple approach is just to simply plot the data. You plot the cost versus the capability score, and in general, you want the alternatives that are in the lower right-hand portion of the curve because those are less expensive and more capable, and you want to stay away from those that fall into the upper left quadrant that are expensive and not that capable. And admittedly, this example that I've shown here is sort of skewed to make the decision easy. Alternative 2 is clearly the best. But what we see more often in reality is you get a line or a series of points that tend to go from the lower left-hand corner to the upper right. So there you're faced with the challenge of saying, well, do I go with cheaper and less capable, or do I pay more for greater capability? If you get into that kind of situation, it might be better to calculate a ratio, or essentially what we're doing with this ratio is normalizing the life cycle cost with respect to the capability score. So there, lower is better. So the lower the cost normalized for capability, the more attractive the option would appear to be. And in this case, so options 2 and 4 are the front runners again. Regardless of what approach you use, again, the point is to make sure that you have a clear and very subjective and methodical approach towards evaluating alternatives to make sure that you're getting the best value for your investment. So once we've gone through all this, and we have designs for the system and for each of its components, we'd suggest developing a master plan to help manage implementation of the project. And one reason for this is that there are a lot of interdependencies in this kind of a project. And there will be certain critical path activities that need to be identified so that the proper sequence of implementation is followed. Also, due to the complexity and in many cases the constraints like capital budget constraints, the project must be spread out over a timeline of several years and ideally would be phased in stages so that at the end of every stage you do have sort of a meaningful and useful improvement that gives your utility value. One other advantage of doing a phased implementation is it gives you an opportunity to pilot some system components. The obvious example here is for online water quality monitoring instrumentation. If you can't buy, if you want to build out to 20 stations, but you only have money in the first year for 5, maybe start with just 1 or 2 different models that are in the running and do a comparison to figure out which one you want to invest in long term during the next phase of the project. And finally, and this is important, we found with a system like this, it's very important to allow some time for preliminary operations before you go live and treat the system as a reliable monitoring and surveillance system. And this gives you time not only to sort out issues with equipment, but also issues with procedures and possibly personnel roles. Let you work through that, and then once you're comfortable that you've ironed out all the problems, then it's the time to go live. So over the years, we've worked with a number of utilities in implementing these systems, and their collective experience has helped us develop this top 10 lessons learned from SRS implementers. And I'm sharing these because they're general enough that I think they might be useful or would be useful to anyone who intends to embark on this kind of a project. The first, and this is probably true of any project, you need to identify a champion, one who's really invested in the vision and going to move it forward. Of course, we need support from senior management, again, especially for something discretionary like this, where you need to make the case for assigning personnel and budget to the effort. On the other end, we need to invest in engage the stakeholders and frontline staff who are going to be operating the system early during the design phase so that what we build is going to be acceptable to them. As Matt pointed out, utilities have a lot of existing capability that will be the foundation of a surveillance and response system. So start by building on those capabilities. Again, develop a master plan and implement the system in phases to stay within any budgetary or staffing constraints. Plan for the learning and optimization period. We covered that. To the extent possible, integrate operation of the system into routine job functions, which makes it less of a burden on the staff who are required to implement the system, and thus makes it more likely it would be sustained. Design the SRS to provide value to routine operations and track performance metrics so that when the time comes, and it will come when you get asked the question, why are we doing this? Why are we spending money on this? You have information to show the value that's being derived from operation of the system. And finally, and I really want to leave with this, is an SRS doesn't have to be complex or expensive. In many cases, you can get an adequate system or a system that meets your goals and objectives without a lot of investment, simply by using information that's already being collected within your utility more effectively, and maybe with a more maybe structured around procedures that help the people who are using that information to investigate and respond to unusual conditions that might be detected in the system. And just to wrap it up, one of the current movements in the water sector is the movement towards smart water or intelligent infrastructure or smart networks. A lot of names for it, but it all amounts to the same thing, which is trying to collect more real-time data at more points in the system about whatever it is you care about, or whatever it is that's going to help you better operate your system or manage water quality. And smart water can take a lot of forms. I haven't seen any single definition that would exclude any of these applications. And I would consider the following to be smart water applications: any form of online water quality monitoring, advanced metering infrastructure, water loss and leak detection, pressure monitoring and management, and the same thing with energy monitoring and management. And I would hold out that an integrated surveillance and response system is just another form of a smart water. In this case, one that's designed to help water utilities detect and investigate water quality problems and prevent them from returning into bigger problems. So just wrapping things up, what we covered today was sort of a high-level overview of a system integration or system design process. These 3 resources can be accessed to take a deeper dive into these topics. The guidance for developing an integrated water quality surveillance and response system goes through the principles of project management, master planning, and information management. The dashboard design guidance document describes requirements for a surveillance and response system-oriented dashboard and provides some nice examples. And in a similar manner, the framework for comparing alternatives presents that alternatives analysis process in the context of designing a surveillance and response system. And then the 2 tools that were discussed today, the Information Management Requirements Development Tool and the Capabilities Assessment Tool, are available on our website. Both can be accessed by visiting this web page, and you'll see that the resources we discussed today are mainly in the system design area of our website. So we'll now go ahead and begin the Q&A session of the webinar. I'm running close on time, but we'll take as many questions as we can. And I'd like to open one final poll question, because we're approaching the end of this webinar series, but we're always open to doing additional webinars on topics of interest in the future. So this is your opportunity to tell us what you'd like to hear about. So we provided 4 canned options that you can select if you're interested in hearing more about those topics. And certainly if you have ideas for other topics that sort of fit within this paradigm of monitoring, surveillance, and response for water quality and contamination incidents, please write those in, share those ideas with us, and we'll certainly keep you informed if we line up some additional webinars in the future. And with that, I'd like to turn it over to Darcy for the Q&A.
Sure. So it looks like we have maybe one question that's come in, Steve. I'm just opening the window. Okay, the question is, I guess it's a write-in actually. One participant is interested in having a presentation on risk communication, but other than that, there are no other questions.
Okay. Well, unless any come in the next couple of minutes, we can probably wrap it up since we pushed people close to the top of the hour.
Okay. Would you like Emily to close the polling question, or do you want me to just go ahead and read through the next slide?
Emily, you can leave that open until we'll close out the poll certainly give people enough time to see the last slide.
Sure.
Well, let's give them another 15 or 20 seconds, and then we'll cover the last slide.
Okay.
Darcy, it does look like one question just popped through.
Okay. Steve, the question is, do you have any recommendations for incorporating future innovative technologies into the master plan?
We're sort of struggling with the same thing, because as a program, we want to keep apprised of new technologies that could be incorporated into this surveillance and response framework. So maybe the most basic and fundamental recommendation is just, read, attend webinars and conferences to keep apprised of new developments and new tools that might fit into this framework. When we started this, AMI was not part of the framework, but we've since incorporated it, recognizing its value to our goals for the program. Likewise, and if you participated in the customer complaint surveillance webinar, you heard that we're also looking at social media monitoring as another tool that could be incorporated into this framework. So I would say, it's just a matter of keeping your eyes open to new potential. And I would invite anybody who has ideas for new components to share those with us, so that we can share that kind of knowledge and ideas with the rest of the water sector.
Steve, there are a couple of other questions. Would you like to cover those now?
Sure. Yeah, let's go as long as people are willing to hang on.
Okay. The next one is, are there any websites for technologies for monitoring distribution systems without invading the SCADA?
Well, there are, if I understand the question correctly, there are certainly third-party services that will essentially collect the data from remote monitoring sites, post it up to a cloud environment that's accessible to utility personnel with credentials. And the systems I've seen are the cybersecurity seems to be robust. Although I'm not an expert in that area, so I would certainly encourage due diligence. But the short answer is yes, you can do it without bringing that data into SCADA. And you can also do it in a traditional way by just putting in parallel communication architectures. Like in one system, their SCADA was mostly hardwired. So we installed a cellular network to pull in the water quality data and brought it into a completely different computer. The computer sat in the control room so the operators could see it, but it was in no way connected to the SCADA system. So there are a couple of solutions out there for doing just what I think the person was asking about. But I don't know of any web. If you want information about that, we do have a communications systems guidance document on our website that might have some ideas and some leads as to where to go to learn more about those options.
Okay. The next question, I think this might be in reference to the tool that Matt presented. The question is, how does this tool help with risk and resilience assessment required by the WIA?
Oh, Matt, I better take this one. So for everybody, the benefit of everyone listening in still, this is a reference to it's Section 2013 of the recently passed America's Water Infrastructure Act. And that section will require water utilities to do risk assessments and update emergency response plans on a 5-year cycle, moving from this point moving forward. I think the first due dates are sometime in 2019. The Capabilities Assessment Tool is not formally part of that risk assessment methodology. And I want to make clear that there's certainly no requirement that the Capabilities Assessment Tool be used to comply with that section of the America's Water Infrastructure Act. However, if your risk assessment tells you that you're concerned about contamination, and if you think that doing improved surveillance and response is a way to mitigate that risk and something your utility wants to pursue, then certainly, yes, I would encourage you to use that tool as a starting point for thinking through what kinds of surveillance and response capabilities your utility would want to invest in. And one last little point, just a plug. Tomorrow, for anybody who is on Water ISAC, a Water ISAC member or on their mailing list, there is going to be a webinar at 3 p.m. Eastern Time that will cover this section of WIA. So if you're interested in that, I would encourage you to find the link to that webinar and sign up.